Today's lesson is on section 6.7, graph linear inequalities with two variables. In this chapter 6, we've done plenty of work with inequalities with just one variable, where maybe we can solve those and graph them on a number line. So for example, I've got a problem right here that looks like that, like we've been dealing with here recently, with just one variable in it, with just x. So x minus 3 is greater than 8. So what have we done with these in the past? Well, we can solve them. And so add 3 to both sides. I can get x by itself. I can get x is greater than 11 in this case. And then if I was going to make a graph of this on a number line to show visually what all the solutions look like, I can graph 11 and some numbers around it just to make sure I'm indicating which direction my number line is going. In this case, it'd be an open circle since I have greater than, so I'm not including that number. So x is greater than 11, so just open circle. And if I'm talking about all the answers that are greater than 11, I'm going to shade towards 12 and towards all of the numbers that are bigger than 11. So that's what my graph might look like for a number line for solving an inequality with just one variable. So we've dealt with those a lot this chapter already. In this last section in the chapter, last section in chapter 6, we're going to learn how to deal with inequalities that have two different variables in it, so x and y. So with one variable, it's kind of nice. Again, I can solve these, make some kind of graph. There is a visual for it. Those work out pretty well. I think we have a good understanding of those. Graphing with two variables, well, what are the solutions, as I kind of ask as a question here, what are the solutions like for two variables going to look like? It is going to be a little different because now I have x and y. Here's an example of what an inequality with two variables might look like. 3x minus y is greater than or equal to 5. So I'm going to need to be able to plug in like an x value and a y value. And this is what this is saying. I need to find out numbers that I could plug into here and here. And I plug those numbers in and evaluate. It's got to be greater than or equal to 5. So if you could probably think about, well, there's going to be a lot of different choices. I mean, I could have a lot of different options for x and y that I could plug in there to get numbers that are greater than 5. It's going to kind of depend, though, because I got to take 3 times x and then subtract y. So I got to choose my numbers carefully. Well, after asking the students a little bit about this and talking about it in class, we'll start to figure out, well, what are these solutions going to look like? Well, think about when do we see x and y together? We see it in ordered pairs, correct? So I'm going to have to pick out a particular x and a particular y, see if that works. Does that ordered pair work in this particular inequality? And I can check that. And then I can, so maybe like for an example, let's say I pick the ordered pair 5, 1. Okay. Well, if I put 5, 1 then into this example I got up here, if I put 5 in, 3 times 5 gives me 15. If I put 1 in for y, it'd just be minus 1. Is that greater than or equal to 5? Yes, it is. 14 is greater than or equal to 5. So yeah, this point would be a solution. But as you're seeing, I could pick out 6, 1. I could pick out 7, 1. There's a lot of different numbers I could pick out. So how do we find all these different answers? Well, the way is I'll keep talking about it, but the students will kind of figure out by using an x and y coordinate plane, there's a nice visual way to show all the possible answers. Just like when we had one variable, we used a number line because we only had that one variable. It's almost like just using the x-axis there. Okay, just going left or right along the x-axis, showing all those answers. Well, now what I'm going to use a x and y coordinate plane, and there'll be a way to show all the possible answers for these inequalities as well. And I'll show that on the coming examples. So kind of like I mentioned in that last page, and something I want you to jot down here if you're taking notes along with me, is that when we talk about inequalities with two variables, our solutions will be ordered pairs, like an x and a y. Before I get into an actual example of showing, okay, well, how can we graph this and show it visually what all the possible solutions are for an inequality, I'm first going to go back to something else we've done in the past, where we've checked to see if a point is a solution or not. How do we do that? We've done this with equations, something like 3x minus y equals 5. If I want to know that is a line, there's some line that would be a graph for. It could be something that looks like this. Just kind of that's not really it. But I'm just kind of making an example. Like that equation has a graph of a line that would fit for it, and I could check and see if one of these points would fall on that line or not. There's a way to do it algebraically. Okay, I could make a graph and actually look at it too, but there's an algebraic way to do it as well. And it is just, I know that like we talked about on the first page, this is an x coordinate, this is a y coordinate for that particular point. So knowing that this could fit in for x, I'm going to plug 4 in for x. I'm going to plug 7 in for y. And I could see if that gives me 5 in the end, and then I would know that solution is, that ordered pair is a solution to this equation. So 4 times 3 would give me 12. Plug 7 in, minus 7. Does that equal 5? Yes, it does. So like this would tell me that, yeah, the 0.47 is a solution to that equation. It would be a point on that line. Well, for inequalities, it's very similar. Again, that's kind of review. That's something we've done in the past. For inequalities, going to the next page here, very similar. If I have some inequality with two variables, 3x minus y is greater than or equal to 5, that same example I've been using, and I want to see if a point is a solution to that inequality, I'm just going to plug in the x and y coordinates from each ordered pair and see which ones do work out in this particular inequality. So like 2, 5, again, that's an ordered pair. That means that it must, if it's some point that works for this inequality, I should be able to plug it in and get something that's true. So put 2 in for x. 3 times 2 would give me 6. Put 5 in for y, so I'd have minus 5. Is that greater than or equal to 5? Well, let's see here. 6 minus 5, I can keep doing stuff on this side. I get 1. Is that greater than or equal to 5? No, it's not. So no, this 0.25 must not be a solution to that inequality. The second one B here, 3, negative 1. If I put 3 in for x, 3 times 3 would be 9. And it's minus negative 1 is what I'm putting in there. So that's kind of like a chop, where I'm going to turn that into 9 plus 1 is what that's going to become. Is that greater than or equal to 5? Yeah, I think it's 10. So yes, this one will be. Okay. I guess I'm doing that in red, but yes, I guess it will be. 3, negative 1 would be a point that would work on that inequality. It would be a point that would satisfy it. And then negative 2, negative 10. Same thing. I can plug negative 2 in for x. I'd get negative 6 when I take negative 2 times 3. And then I'll put negative 10 in. So again, it'll be like a chop situation. And I'll get 10 here. Is that greater than or equal to 5? Well, negative 6 plus 10 gives me 4. Is that greater than or equal to 5? Not quite. So no, this one would not work. But again, just showing that you can plug answers in to see if they would be solutions to that inequality or not. Now we could do this for a bunch of different points and try to find all the solutions that work for an inequality, but that would take a really long time. So there is an easier way, and it comes from kind of the visual way that we do an inequality. In this case, from graphing. As I've got up here is a few notes to kind of reassure you that graphing these is still a lot like graphing equations, and we'll use some of those strategies. But those are kind of little, three little notes I'd like you to jot down about graphing inequalities. It's like graphing equations. In this case, though, the line may be part of the solutions, or it may be just a boundary. And the solutions are either on one side of the line or the other. What I'm going to compare this to is just like when we graphed that first inequality. So I think the very first problem I had up here for you was something like this, correct? Where I had this inequality with just one variable. We solved things like this. I added 3 to both sides. I got x is greater than 11. And then I made the number line graph where here's 11, here's 10, here's 12. It'd be an open circle, and I want to shade numbers that are greater than 11. So recall this from the first page that I started these notes with. Well, just like this, look at my second note here. Sometimes when we're graphing with inequalities, the line may be part of the solutions, or it may be just a boundary. Same thing happens here. Number 11 is kind of our key number. But notice, like, number 11 isn't part of the answers, is it? In this case, I have x is greater than 11. So could x be 11? Is that one of my answers? No, it's not. So how do I show that? Okay, well, I show it just by leaving the circle open. I'm saying it's like a boundary, okay? I started at 11, but 11 isn't one of my answers. So that's going to be kind of like we do for one variable. And same thing with the second bullet point here. The solutions are either on one side of the line or the other. Well, that same thing happened down here. Okay, in this case, it was all greater than, so I shaded to the right. So my solutions are either going to be on one side of that boundary or the other side, and I'll show you how that looks. So, going back to a problem here that I have. Y, in this case, we're going to graph this inequality right here. It's got two variables. Y is less than 2x minus 3. The first bullet point now kind of comes in. It's just like graphing equations. Remember, we know slope-intercept form. Y equals mx plus b. So I'm going to write it just like that for a second to show us that it is going to graph just like this. Actually, here I'll put even y equals mx plus b up here, just as a reminder. See, it does fit this mold. Oops, not 3, but I want b there. It does fit that form of the equation. So remember in this case, well, I'd put my slope is 2, and my y-intercept is -3. So how did we graph something knowing those pieces of information? Well, my y-intercept's -3, so on the y-axis, I'm just going to go down 3 from the origin, put a point. And then if my slope is 2, that's kind of like a rise over run of 2 over 1. So I'd go up 2 and over 1, up 2 spots over 1, up 2 over 1. Okay. So just like graphing an equation, very similar. Now, here's where it gets different for an inequality. Like we talked about with point number 2, sometimes the line is part of our solutions, or sometimes it's just a boundary. Just bringing my graph back here quickly. Remember, I had an open circle around 11, and then I shaded to the right. Okay. Well, in this case also, in this problem, I've got a less than sign. It's not less than or equal to, correct? It's just less than. So what we're saying there is just like in this case, okay, that key number wasn't part of the solutions. Same thing with this line. It's not actually part of the solutions. How do I show that? Is I just make a dashed line. As opposed to a solid line, I'm going to make a dashed line through all these points. Okay, I still need to graph this equation, and it looks like this, but when it's just less than or when it's just greater than, I'm going to make a dashed line. Very similar again to when I had an open circle on my number line problems. So that kind of falls in place, very similar to that. Then, just like we talked about point number 3 there, my solutions are either on one side of my boundary or the other. They're either they're all greater than or they're all less than, remembering from this. Same thing here on the graph too. All my solutions are either going to be above this line or below the line. And there's 2 ways you can check it out. One way is just by picking out a random point and checking to see if that point works in the inequality, kind of like we did for some of those first examples. So I'm going to make some room for myself here and then show you that. So let's say like the point 0, 0. Here it is. I'm going to color it in red. There's the origin. Okay. Well, if I plug that point in, 0, 0, plug 0 in for x and 0 in for y, and I get something that's true, that means 0, 0 would be a solution. And if 0, 0 is a solution, then all the points on the side of 0, 0 must be a solution as well. So this is one way I can do this. I can just plug in a random point, see if it works. Let's see what happens when I plug in 0, 0. I'll get 0 is less than, well, 2 times 0 would be 0 also, minus 3. So I got 0 is less than -3. So is 0 less than -3? And I'd say no, it's not. Okay, 0 is not less than -3. So what we found out is that 0 is not one of the solutions. Well, if 0, or the origin I should say, the origin is not one of the solutions. So if the origin is not one of the solutions, then none of those points on that side must be a solution. So it's got to be all the points on the right side, or kind of below the line in this case, I would say. All these points must be the solutions. I could pick one of those randomly and just double check to make sure. Let's say I have a point way over here, right here. It looks like I have the point 50. Okay. If I put the point 50 in, given where I shaded, that should work. So the point 50. Well, 0 goes in for y. That's less than 2 times 5, which would be 10 minus 3. 10 minus 3 is 7. Is 0 less than 7? Yes, it is. So just kind of showing you that this is one way you could do it. There's another way too, but one way you could see which way to shade the line on, or which way to shade for all the possible solutions, is just by checking a random point. One more kind of set of bullet points here, or important notes I want you to copy down, is if you're kind of a concrete person and you like some steady directions, something, okay, well, how do I do these problems? Well, here's the steps to help you graph an inequality. Here's the exact steps I would have you follow, and exactly what I'm going to do. So number 1, first you're going to graph the equation using either the slope-intercept form or the intercepts method, whatever one works better for that problem. Then 2, as you graph your line, make sure you know if it should be a solid line or dashed line, as we'll talk about. We did an example there where the first one was dashed. We'll talk about a solid line as well in this example. And then number 3, like we said, check a point to see where side the solutions are on. That's one way you can do it. So, looking at this example, I'm just going to pull it over here. It says graph the inequality. I'm just going to pull it into my open space. I'm going to keep using slope-intercept form for this one because it's got y with, there's stuff on the same side as y, but if I just add this 2x to both sides, then it's very quickly in the slope-intercept form. So I'm going to use that form in this case. Y is less than or equal to 2x plus 1. So now graphing this inequality, again, is just like graphing an equation. I could pick out the slope like we've done in the past, and the y-intercept. The y-intercept would be 1 in this case, so I'd go on the y-axis and go up 1 from the origin and put a point. The slope, again, if I was doing rise over run, I could say it's like 2 over 1. So up 2 over 1, up 2 over 1, up 2 over 1. For this particular problem, I have less than or equal to. So again, remember when we did a number line, if you had less than or equal to, in this case you would shade in the dot. Okay. Well, similar to that, in this case we're saying that the line then is part of our solutions. So in this case we'll make a solid line. That first example we made a dashed line. In this case we'll make a nice solid line, just like a line like you usually would if you're graphing with a ruler. So I make a solid line. That's telling me that all the points on that line are also possible solutions. Then again, the last thing to do is we got to shade on just one side or the other, so I can check a random point. And just one small thing to make sure we understand, though, don't check a point that's actually on the line. You have to check some point that is somewhere else. So for example, here I'm going to check the point 2, 0. The origin's usually a pretty easy one to check as well, but in this case I'm going to check 2, 0 and see what happens. If I put 2 in for x, so this is the point 2, 0. So I'm going to put 2 in for x and 0 in for y and see what I get. Well, I put 0 in for y. That's less than or equal to 4 plus 1. And so in this case, let's see, 4 plus 1 gives me 5, so 0 is less than or equal to 5. Is that true? Yeah, it is. So 2, 0 must be a point that works. So then all the points on this side must be solutions. So I would shade in all the points on this side of the inequality. And there would be the graph showing all the possible solutions for this inequality. If I check any point, any random point over in the red scribble area here, all these should work in that inequality. I'll go through just one more example here showing this one, because this one also says graph the inequality, but it's set up nice for intercepts method. So I'm just going to show one more, remind us how we graph with intercepts method. Okay. So it's got x and y on the same side. So remember how I usually do this in class is I'll make a little table, and I'm going to say I'm going to plug in 0 for x and I'm going to plug in 0 for y and solve those two little mini equations I get then. If I put in 0 for x, it kind of cancels this term out, or actually it just does cancel that term out, and I would have this little equation 2y equals 6. If I solve that, I'd get that y equals 3, so that'd be one of my intercepts. Going back to the original equation, if I put in 0 for y, it would cancel this term out. I'd get 3x is equal to 6. Divide both sides by 3. So then I'd get x equals 2. So my other intercept would be 2, 0 for my x-intercept. And so that's kind of a nice handy way I can find 2 points to graph. 0, 3 would be right here. 2, 0 would be right here. What type of line should I have in this case? Should I have a solid line or a dashed line? Well, looking at my inequality, it's greater than. It doesn't have the line underneath. It's not greater than or equal to. It's just greater than. So that tells me that the line is not part of the solutions. So I'm going to have a dashed line in this case. And then my last step is I just need to check any kind of random point to see where the solutions would be. Again, just like for linear inequalities with one variable, we always had the solutions on one side of the line or the other. So same thing here. So I just need to use one point. Again, usually the origin's an easy one as long as the line isn't going through it. So I'm going to use the origin. If I plug in 0 for x and 0 for y, I get 0 plus 0. Well, is that greater than 6? So, well, is 0 greater than 6? No, it's not. So in this case, 0, 0 is not one of the solutions. So that means none of the points on this side of the line must be any of the solutions. So they must all be on this side. So I would shade in above the line in this case. Again, just kind of showing one more time that this must work then. If I just pick any random point over here, let's say I pick the point, it looks like 9, 9 is up here. If I put 9 in for x, I'm going to get 27 here. Plus 9 in for y gives me 18. Is that greater than 6? 27 plus 18? Yeah, that should be great. I think that's going to be 45. That is greater than 6, so it does check out. So again, graphing these still a lot like graphing inequalities with one variable. Just a few other things to consider, but they do relate to each other very well.